everyone. This is the Indian Academy of Sciences, the Academy Trust, celebrating the India International Science Festival and the Frontiers of Science lectures. Today we have Professor Ken Ono, a very renowned mathematician, speak to us on why does Ramanujan, the man who knew infinity, matter? Let me introduce Professor Ken Ono. Professor Ono is a Thomas Jefferson Professor of Mathematics at the University of Virginia. He is currently the Vice President of the American Mathematical Society and the Chair of the Mathematics section of the American Association for Advancement of Science. He did his PhD from the University of California, Los Angeles in 1993. Professor Ono specializes in number theory. He is widely published. He's published over about 200 papers. In particular, he is known for his expertise in integer partitions. He has solved many puzzles and conjectures of Srinivasa Ramanujan. The name Srinivasa Ramanujan rings a bell on this day. It is on the eve of Ramanujan's birthday that we are having Professor Ken Ono's lecture. Tomorrow is Ramanujan's birthday, and we will celebrate that birthday as the National Mathematics Day. So it is deliberately we have done this on the eve of Srinivasa Ramanujan's birthday or the National Mathematics Day. Tomorrow we will have another lecture in celebration of the India International Science Festival and the National Mathematics Day. Professor Ono was associated with various kinds of activities, and he was an associate producer and mathematics consultant on the biographical movie on Srinivasa Ramanujan, which is also entitled, the book is entitled The Man Who Knew Infinity, so is the movie, and Ken Ono is the co-producer and the mathematics consultant on that movie. He also wears another hat. He's a fantastic athlete, and he represents US in various triathlons and has been doing so over the years. And he is in the World Cross Triathlon Championships. He has been an Alfred Sloan Fellow and a Guggenheim Fellow. He's also received the Presidential Medal, Presidential US President's Career Award from President Bill Clinton in 2000 for his work, which is on cracked partitions. Professor Ono has been named the 15th most influential mathematician in the world. So it is a matter of great pride and privilege for us to have Professor Ken Ono deliver this lecture to us. As a matter of fact, for those of you who may not know this, we have also had the honor of Professor Ken Ono visiting us in India just about a year ago as the Jubilee Chair Professor of the Indian Academy of Sciences. And I was very proud to host him in India, and he's traveled to several institutions in India as the Jubilee Chair Professor and has given talks. So it is with a matter of great pride, honor, and delight that I'm happy to host Professor Ken Ono one more time, this time virtually from the podium of the Academy Trust, primarily in celebration of the India International Science Festival. The rest of the event today will be conducted by Professor Tirthankar Bhattacharya, Professor of Mathematics at the Indian Institute of Science, but more importantly, he is the chair of the outreach program of the Academy Trust of the Indian Academy of Sciences. Over to you, Tirthankar. Please take over. And again, thank all of you for joining this program. And I take this opportunity once again to thank Professor Ono for engaging with us, and to Professor Tirthankar Bhattacharya for organizing this event and conducting this event. Thank you very much.
So we are very glad to host Professor Ken Ono, and it's over to you.
Okay. All right. Hello, everyone. For me, it's morning in the United States. So good morning to me. Good late afternoon, I think, to all of you in India. Thank you very much, Professor Majumdar and Bhattacharya, for arranging this lecture. Your words are too kind, Professor Majumdar. Without Ramanujan, I don't think I would have very much to talk about. So I think the best way to begin this lecture is to take this moment, which I understand you do every year, to remember a giant in science. And so the point of today's lecture is to answer this question that you see on the slide. Why does Ramanujan, the man who knew infinity, matter? And I hope by the end of this lecture, I will have offered you 3 or 4 answers. And I hope you agree that with some of them, hopefully all of them. And let me get started. So I first learned about Ramanujan a long time ago in 1984. This letter came to the house. I grew up in the suburbs of Baltimore, Maryland, where my father was a professor also of mathematics at Johns Hopkins University. And this letter came at a time when I was a high school student who didn't like mathematics. Actually, I didn't even like school. And to be completely honest, I didn't really want to be or do anything that my parents thought would be best for me. Typical teenager who was kind of lost. That would be me. And although I was doing very well in my mathematics courses, for me, mathematics was the stuff of tests. Can I get a perfect score? Can I finish exams quickly? And I don't think that's very unusual for children growing up anywhere in the world over the last 50 years. They think of exams, problem sets, and that's what first comes to mind when one thinks of mathematics. Any event, on Saturday, April 7th, 1984, this letter was sent to my father, and I gave it to him. And a few hours later, he comes to me, quite emotional, and he said, I have to tell you this amazing story, and it's related to this letter. And, well, let me read the letter to you, because if you were me, I was in high school at the time, you would find this story quite remarkable. The letter reads, Dear Sir, I understand from Mr. Richard Askey, Wisconsin, USA, that you've contributed for the sculpture in memory of my late husband, Mr. Srinivasa Ramanujan. I'm happy over this event, and I thank you very much for your good gesture and wish you success in all of your endeavors. Signed, S. Janaki Amal. And for me, as it is with all of you, this letter was not really intended for my father in particular. This was a form letter that was clearly sent to a large number of people. And so I found it quite strange that this letter would mean so much to my father. So what did I learn? I learned that as a starving graduate student in Japan, right after World War II, that's the age of my father. Japan, as you know, did terrible things in World War II. World wars are terrible. And as a struggling student in wartime and post-World War II, times were very difficult. There were food shortages. There was the universities had to be rebuilt. And so my dad had to overcome many difficult hurdles to end up becoming a professor in the United States, much less just finishing a degree. And I learned that one of the inspirations for him was an Indian man named Ramanujan, whose ideas came to him as visions from a goddess, and a man whose ideas were completely his own, who his ideas represented absolutely extraordinary creativity. And to top that all off, Ramanujan, I learned, was a man who had dropped out of college twice. And for me, this letter is meaningful because, well, my father, who isn't very emotional, clearly held Ramanujan in very high regard. And this was the first time that I heard that the quality of someone's work, not speed on exams and accuracy, the first time I heard that creativity, the first time that I heard that doing well in school is only one measure, but the most important measures are the quality of one's character and the depth of the legacy of one's ideas. That's the first time I ever heard that from my parents. And I took a lot of hope from that because, in the long run, as I know now, nobody will care what your test scores were like 30 years from now. And I needed to hear that at that age. And that marked a very important moment for me. So the first time Ramanujan mattered to me was the legend. And it didn't even matter what the theorems would be. It didn't even matter about the story and the cultural implications. It was the principle that unbridled creativity should be inspired instead of being constrained by a very rigid educational system with rather mundane metrics. So that was very important to me. Together with Amir Excel, who is a popular science writer, we wrote a book called My Search for Ramanujan, where many of the things that I'm going to describe in this lecture are outlined. And if you're interested in that, I encourage you to check this out of the library. And it was very important for me. It was a cathartic experience for me to sort of relive all the points in my life where Ramanujan mattered. And and this letter is how my story with Ramanujan begins. As was mentioned earlier, Ramanujan matters to me largely because I had the luxury, the great opportunity to participate in the production of a Hollywood film about Ramanujan. That doesn't happen if you're trained as an ordinary, pure theoretical mathematician, but I'm so grateful to the Pressman family, the Pressman Film Company, together with IFC Films and Warner Brothers. They saw to it that this film about Ramanujan and his life was made in 2015. And it was one of the richest experiences of my life, trying to think very carefully about why the world should care about a mathematician. And that was a challenge for us because none of us were really in the business of making films. And despite what anyone may think of the film, I think it was very important for us, and we were very proud of the final product. The idea was not about making a Hollywood blockbuster. The goal of making The Man Who Knew Infinity was to help make Ramanujan a household name in the world. So here is a photograph of one of our film posters that is next to the famous postcard photograph of Ramanujan. So as you can see, we cast Dev Patel to play Ramanujan, and we cast British actor Jeremy Irons to play G.H. Hardy. This film was largely based on the fabulous biography, also entitled The Man Who Knew Infinity, by Robert Kanigel. What I liked about one of the things that I enjoyed most about this production, and that was a source of concern for me at the outset, was whether or not the actors and the producers and the director wanted to tell the story from the story with a true scientific perspective, right? How much care would be taken to depicting how mathematicians talk, how mathematicians think. And this is what I was alluding to earlier when I said that the actors really wanted to know how to portray mathematics and mathematicians. And so here's a picture of me training with Dev Patel, learning about how you would talk like a mathematician. So I actually gave lectures, the actors watched, and we practiced. So here we are practicing a short discussion in complex analysis on the Cauchy integral formula. And I'll tell you, I didn't know how actors learn to act, but based on this experience, it's clear to me that the best actors really are very skilled in terms of portraying others. And Dev and Jeremy, I think did a fantastic job. So the lecture is called "Why Does Ramanujan, the Man Who Knew Infinity, Matter?" All right. Well, right now the world is suffering through an awful pandemic. This pandemic impacts the entire world. The world actually, before this pandemic, was already facing many challenges, right? There's population growth, there's climate change, there's the need for development of green energy, There's the questions in terms of searching for cures for cancer, so on and so forth. There's so many challenges that we face in this world that are global concerns. And all of the global concerns that I've mentioned to be addressed require science. And the best science requires cooperation between experts from various scientific disciplines. But on top of it also requires collaboration and cooperation from people all over the world, from different cultures, different backgrounds, different religious beliefs, so on and so forth. And one of the reasons that the film and the story of Ramanujan matters is the simple fact that the story of the relationship between the genius Ramanujan, this incredibly talented mind that needed some mentoring, the story, the collaboration between the English professor and the Indian scientist represents to us what can be achieved through cooperation. Now, there are other lessons that I'll expand upon later, because this was, of course, not a perfect relationship. The relationship between India and England at the time was abominable. But if we just focus for the moment on the extraordinary fact that 100 years ago, Hardy and Ramanujan found a way to collaborate and produce volumes of first-rate science, is a reason why Ramanujan matters. So what you see in this picture on your screen is a photo from almost exactly 4 years ago today. Actually, 4 years ago at the end of October. In 2016, Barack Obama invited many scientists to the White House to train the transition teams for the Clinton campaign and the Trump campaign to the White House, to train them on the various scientific arms that would be available to them in the federal government. So this is tradition. The outgoing president offers a series of events that trains the incoming transition teams, trains them about the affairs of the government and the White House. And Obama asked us to be the social event that was the conclusion of a full day of lectures on science. So I lectured on mathematics and STEM education. On the left was the former NSF director, National Science Foundation director, Franz Cordova. And we were delighted that the President, Obama, invited us to screen the film, The Man Who Knew Infinity, as an opportunity to emphasize the importance of not only science and pure research, but of course to emphasize the need for international cooperation because of the story of Ramanujan and Hardy. And we were delighted to be there. And this is a picture of DJ Patil, who is a distinguished data scientist. DJ and I are live streaming a problem to the citizens of the United States, which is, what is the smallest number that is the sum of two cubes in two different ways? And as you can see, Jeremy Irons took time out of his very busy schedule to participate in this event. And we were proud that our film was used and the story of Ramanujan was used to emphasize the need for global cooperation in science. That is another reason that Ramanujan matters. His story inspires, as I said earlier, students, and his story inspires policymakers so that the public and policymakers and government officials can understand the importance for investment in science and education. So this is a lecture that I give to many kinds of audiences, so please bear with me when I repeat things that I know you all know. Instead, please think of it as my Western perspective on Ramanujan's life. I won't get things right. I didn't grow up in India. I try to visit once a year. But this is my brief synopsis of his storied life. So Ramanujan was born in the late 19th century in lush southern India in the state of Tamil Nadu. He was born a Brahmin. This is how I generally describe this as the the cerebral or priestly caste. It won't come as a surprise to anyone that he was an outstanding student as a young boy. If you visit his high school in the town of Kumbakonam, they will share with you the awards that he won, including a certificate indicating a scholarship to college. And one of the things that I like to say, because it gives some insight into who Ramanujan was, as a young boy, he was already fascinated with mathematics. He did a lot of his exploration on his own. And as we've come to understand it from the writing of others, that he discovered much of trigonometry himself by the early age of 13. However, when he discovered that trigonometry had been invented before him, he was upset by this fact, and he threw his notebook onto the roof of his house. That spirit, that confidence in one's own abilities is a treasure. Overconfidence is not a good thing, but belief in one's own ability to succeed is a trait that we should emphasize a bit more. In college, a lot of the students that I teach are just doing their very, very best to satisfy instructors. But if you go back in time and interview these kids when they are 6 or 7 years old, all of them would say, yes, I'm really good at math, or I'm good at writing, or I run very fast. Where is it along the way in our rigid educational system do we lose often that self-confidence? And so I really enjoy telling the story that Ramanujan, as a young boy, was very confident in his ability. In fact, if I had the ability to go back in time and ask him this question, I would suspect that he wouldn't even understand the point of the question, because he was already beyond any notion of self-doubt or self-purpose. As a young boy, he received a book. It's called A Synopsis of Elementary Results in Pure Mathematics. Not a great book. It's really a book that was used by English tutors to prepare students for exams, a book by G.S. Carr. But despite that, Ramanujan became fascinated by mathematical formulas, the formulas that he found in this book. This book is described as a list of over 6,000 theorems, systematically and quite scientifically arranged, but with no proofs. And as an amateur, Ramanujan felt that this is how mathematics was recorded. So this large plethora of formulas ignited Ramanujan's passion for mathematics. He began finding his own formulas, and following the style that he saw in Carr's book, he began to assemble his own notebooks. These notebooks survive to this day, and if you ask very nicely at the library at the University of Madras, you can ask the librarian to bring out the notebooks and you can flip through them. This is me, I think 6 or 7 years ago, with Professor Raghuram, who is at ISER Pune, and here we are flipping through Ramanujan's 3 notebooks. I have to say, I have of course flipped through reproductions of these notebooks many times. For the first time in the early 1980s, and I have to say that each time I go through the actual genuine notebooks, I still feel like I learned something, despite the fact that I've seen these formulas over and over and over again. And if you work in mathematics like I do, the only analogy that I can offer you is that each time I read these notebooks, I feel like I'm reading a holy manuscript that is written in such a tight way that only from time to time am I allowed to see or earn a little glimpse of a theory that I missed before. It's a very special book in that way. One thing I have to mention is that these were Ramanujan's personal notebooks. He didn't write them for us. And so that extra layer of mystery certainly adds to the excitement as well as the frustration when we know we will never get an answer to the question, I wonder what Ramanujan had in mind when he wrote down this formula, right? That's that if there's a question that I'm going to be asking almost every day of my life for the rest of my life, it will be that question. What did he think of? What was he thinking on in chapter 9 of, you know, this work on such and such? So Ramanujan became obsessed with mathematics. He spent all of his time doing his mathematics. And as a result, he was unable to focus on his studies in college. So he flunked out twice. He spent, and this is something that I have to explain to Westerners. He spent much of his time in the Hindu temples where he lived. There's a beautiful temple in the town of Kumbakonam, the home of the Mahamahan festival. The Sarangapani Street Temple, which is only a few blocks from his childhood home, is really a wonderful place to visit. So I like to mention that. Despite his struggles in college, he found work as a clerk. And I think that is another important thing to emphasize, that back in the day, over 100 years ago, failure in college doesn't make you a failure. He had people who continued to support him, who believed in him. And that is another little lesson that I like to emphasize about this story. You see, if Ramanujan had been lost to the world of science, if his notebooks had never seen the light of day, what I have to emphasize is that would lead to a future, his future, that I would not be able to comprehend. What mathematics would look like, what physics would look like, what certain applications in electrical engineering would look like, those aren't questions we would want to answer. And so the fact that he had supporters continuing to help and assist him when he was a 2-time college dropout is a very important part of this story. One fact that was absolutely clear to us in the present day is that certainly no one could comprehend the implications of the formulas that he recorded in his notebooks. Why is that a fair statement? If I were to circulate his notebooks to university professors all over the world today who have not studied his works, I think that well over 80, maybe over 90% of professional mathematicians today would struggle to make sense out of his formulas. And I regret to say that I think most would dismiss his formulas as the work of a crank. All right. And so there is a lot to the story of Ramanujan that we should be very grateful for, because it could have almost never happened. So in this lecture, I'd like to show you a few film clips to spice up the lecture. And the first film clip I'd like to show you is how we depicted mathematics as an art, right? We made a film. The film should be meaningful to a wide audience, not just an audience of mathematicians. So very early on in the film, we needed to make it very clear that mathematics could be viewed as an art, the stuff of poetry and music. And in this scene, this is how we portrayed Ramanujan's view of mathematics. And at the same time, we wanted to emphasize that Ramanujan was isolated. He was alone, and he was desperate for companionship mathematically. He wanted to share his ideas with others. And these are the two main takeaways from this scene.
Go ahead. You can look. Please.
What does it all do?
It's like a painting, I think. Only imagine it is with colors you cannot see.
What good is that?
Not much for you, I'm afraid. But for me, it is everything. Maybe there is someone else who can see and understand it as well. and for them it will be important.
Have you met them?
No, not yet.
I want to understand more than just colors I can't see.
What do you see?
Sand?
Yes? Imagine if we could look so closely that we could see each grain, each particle. You see, there are patterns in everything. The color in light, the reflections on water. In maths, these patterns reveal themselves in the most incredible form.
So there is that scene. That's how we wanted to actually use the beautiful nature just outside of Kumbakonam, where this scene was filmed, to illustrate how mathematics could be viewed as beautiful. And of course, you see that Ramanujan is desperate. He is looking for and seeking someone who he can share his mathematical ideas with. As I'm sure you know, Ramanujan then reached out for help. He wrote letters to mathematicians in England. One was to G.H. Hardy, who responded. And the letter that he wrote to Hardy begins with very famous words. I beg to introduce myself to you as a clerk. I've had no university education. I've not trodden through the conventional regular course, but I'm striking out a new path for myself, and the results I get are termed by local mathematicians as startling. Very accurate words. Here is a photo on the left of G.H. Hardy. I first learned of Hardy in high school, not through his mathematics, but through his role in helping assemble the famous Hardy-Weinberg law in genetics. Hardy was the consummate pure mathematician. He was embarrassed to participate in applied mathematics. So it's quite ironic that one of his scientific results that is most well known is a formula in genetics. On the right is Jeremy Irons in the same pose. And although Irons was much older than Hardy when this picture was taken, I think the resemblance is pretty good. Very close, very close. What was in the letter that Ramanujan sent to Hardy? So there were many things in this letter. There were 7 or 8 pages of mathematical formulas that followed those very beautiful words. Some of the things that Ramanujan wrote to Hardy in these letters would make you think he was absolutely crazy. There is the claim that the sum of the positive integers, 1 plus 2 plus 3 plus 4, so on and so forth, there's the claim that that's not even positive infinity. It's not even positive. Ramanujan claims that he had found a theory where adding up the positive integers in order is just negative 1/12. How random does that seem? Now, what's interesting about that is that Hardy, as an analytic number theorist, was familiar with the groundbreaking work of Riemann from 50 or 60 years earlier. And it turns out that there's a way to make this formula almost reasonable. And it makes use of what's called the Riemann zeta function, which is the object that is at the heart of the $1 million prize problem called the Riemann hypothesis. And Hardy was certainly surprised to see that the untrained Ramanujan, by his own devices, whatever they turn out to be, had recovered glimpses of what Riemann's theory offers. So there is a way to make this formula almost reasonable, and it's called the theory of the analytic continuation of the zeta function. So here is a scene from the film where Hardy is really struggling with the mysterious letter. And so let me show you, let me just play this for you. So this is Hardy the day that the letter arrived from Ramanujan.
You know, Littlewood, this year alone, I've received correspondence from those who profess to prove the prophetic wisdom of the pyramids, the revelations of the elders of Zion and the cryptograms which Bacon supposedly buried within the plays of the so-called Shakespeare. But a letter from an ill-educated Indian clerk in Madras challenging assertions I made in the track series really takes the biscuit.
Well, I have to say, I've made similar assertions myself.
So you admit it?
But this was 3 years ago.
No, I'm talking about the letter. Bloody brilliant, I thought. I don't know where you got the postmark. Almost had me fooled.
I simply don't know what you're talking about.
Oh, come on. I'm not a complete idiot.
I don't know how to get this into your thick skull, but whatever it is you're talking about, I'm simply not involved. Play.
Sir, you've missed Hall.
Not hungry.
I tell you, there is a war coming, no doubt about it. Because we are being led like mindless, spineless sheep, and no one bothers to question any of it. It's coming all right, you can smell it.
You're as paranoid as Hardy.
With all due respect, Bertie, you couldn't hold a candle. Littlewood, could I have a word?
Yes, of course. Integrals, infinite series, God knows what else. Oh, excuse me. I always forget you don't believe in a supreme being.
All right.
This chap turns out to be genuine. You might have to reconsider.
Oh, he must be genuine. Who'd have the imagination to invent all that?
Well, I'm rather flattered you thought I did. These two infinite series are the more intriguing.
Yeah, they defeated me completely. I've never seen anything like them.
Well, it's deceptive. I'll wager the hypergeometric series.
A great Littlewood stumped. He's Hobbes class, I'd say. Being inexperienced, I would very highly value any advice you give me. Yours truly, S. Ramanujan.
What does the S stand for?
You can ask him yourself.
You intend to invite him here?
Well, no. Much better let him rot away in his office in Madras.
Well, there you have it. Hardy was so struck by the letter that at first he thought it had to have been a hoax perpetrated by his good friend John Littlewood, played by actor Toby Jones. So as you heard, Ramanujan was invited to study in Cambridge. It was really an extraordinary invitation at the time, keeping in mind the history of the day. And although Ramanujan at first did not accept this invitation, he finally did accept the invitation after some deep consideration. And what I'd like to show you here is that depicts the first meeting that he has with Hardy in his office in Cambridge. So let me just add a little to this. What you saw in the last scene also were some interesting facets about Hardy as a person. He was very arrogant. He thought very highly of himself. And he was also an atheist. He didn't believe in God. He thought so highly of himself. In fact, this is very well known. He thought so highly of himself that he thought he was in a personal feud with God if there ever happened to be a God. And so I think it's very interesting to recognize that such a person, someone as unusual in his constitution as Hardy, would be the one to discover Ramanujan. So here is our scene depicting the first meeting that Ramanujan has with the Cambridge professors.
Ramanujan, we decided that for the good of everybody, you should attend some lectures.
But I'm here to publish.
Yes, all in good time, I hope. But first we need proofs of your work.
It's really nothing to worry about. It's simply a question acquainting you with the more formal methods that will benefit our future work together.
I mean, we need a common language. You wouldn't expect us to converse with you in Tamil.
No, but you expect me to speak English.
Quite. So, there'll be plenty of time for publishing.
I'm sorry, but with all humility, how does anyone know that? I don't want this to die with me.
I assure you it won't.
Thank you, sir. But I have much more to share with you. As I told you, the letter only contained a small sampling of my discoveries. You'll see I have even found a function which exactly represents the number of prime numbers less than x in the form of an infinite series.
Exactly.
Yes, I thought if we were going to publish, it should be something groundbreaking.
Well, this is most unexpected.
Hardy, this will take a lifetime.
Maybe two.
Okay, so there you have it. At the time Ramanujan showed up in England, in Cambridge, Hardy and Littlewood and the other English professors only had seen a small collection of Ramanujan's formulas, just the formulas that he had left and written in his in the letters in their correspondence. By the time he arrived, as you now know, he showed up with 3 notebooks. So there you have it. To set up the film, what first captured the interest of Irons and Dev Patel to play these roles was the very interesting human story between these two men. Two very different people from different cultures, a Hindu, untrained mathematician, a supreme talent in Ramanujan, and in Hardy, the consummate British Don, elite professor who knows how science should be written. And both would benefit from working with the other. And on top of that, the cultural differences made for the compelling story that attracted the actors to this story, to this project. The last film clip I'd like to show you has to do with another very important answer to why Ramanujan, the man who knew infinity, why Ramanujan matters. As I've said, Hardy had a very difficult time understanding and first beginning to communicate with his talented student, mentee in Ramanujan. And as a university professor, we see students all the time. And I have to tell you, at least from my experience, I still agonize over some of the most talented students I've had over the years who I felt like I didn't actually connect with. Maybe I could have done better. Maybe I could have encouraged the student in a slightly different way that would have resulted in a more positive experience. These are things that are natural human concerns for students and teachers, parents and children, anytime there is a mentoring relationship. And because Ramanujan was such a special case, I like to go back to the question, where would we be today in science had Ramanujan's ideas never been brought forward? And as I said earlier, that is a frightening thought to me. And so one of the important lessons that we learn from Ramanujan is that when you are in a position of mentor, that is a great responsibility, not one to be taken lightly. And although Hardy was very set in his ways, even Hardy had to think very deeply about how he could properly care for and motivate and inspire the supreme talent in Ramanujan. And so in this scene, it's a beautiful one. I'm very proud of it. I want to illustrate the importance of having a flexible mentor, one that can really benefit someone like Ramanujan or any talented student.
How did you know that theorem?
It came to me. Mr. Hardy, I don't understand why we waste our time doing all these proofs. I have the formulas.
It's not that I can't see what you've claimed. It's that I'm not sure that you know how you got there. Or indeed that your claims are correct. There are subtleties which...
But they are right, sir. I have more important new ideas.
Yes, but intuition is not enough. It has to be held accountable. And a little humility would go a long way. Why do you think they want us to fail?
Because I'm Indian.
Well, yep, there is that. But also because of what we represent. Now, Euler and Jacobi, who were they?
Mathematicians.
Just names to you. Euler was the most productive mathematician of the 18th century. Most of his work done after he was blind. Jacobi, like you, was snatched from obscurity and was almost as impressive as Euler. Now, I think you are in their class. What they had in common, what I see in you, is a love of form. It's all through your notebooks. Let me ask you something. Why do you do it, any of this?
Because I have to. I see it.
Like Euler. Form for its own sake. An art unto itself. And like all art, it reflects truth. It's the only truth I know. It's my church. And you, just as Mozart could hear an entire symphony in his head, you dance with numbers to infinity. But this dance, this art, does little to endear us to certain factions who see us as mere conjurers. So if we are going to challenge areas of mathematics that are so well trod, we cannot afford to be wrong. I need you to attend your lectures, don't offend your professors, and keep doing your proofs. Otherwise, this experiment of ours will be doomed to failure. Come with me. I want to show you something. There are many ways to be honored in life. For us, being elected a fellow is certainly one, but in my humble opinion, to leave a legacy here at the Wren after we're gone is the greatest. This library houses the epistles of St. Paul, the poems of Milton, Morgan's Bible. But in my estimation, as a man of numbers, the pièce de résistance is Newton's Principia Mathematica. Now, just as Newton represents the physical aspect of our work, your notebooks represent the abstract. It took a long time for Newton to be proved, which is why we have an obligation to prove these. And if we do, I believe that one day, these notebooks will find their place here. Now, do you understand what's at stake here? Good.
Okay, I think the scene sort of speaks for itself. So if you kind of get the sense of what I'm talking about, when I was a student, I needed great professors, not necessarily great scientists, although they were, in my opinion. But you certainly, as a student, learn so much from your mentors. And let's face it, a strong mentor can really guide you and help you on your way, not only in terms of academic content and science, but in terms of one's self-belief, one's confidence. And, there was so much in the life of Ramanujan that could have gone wrong. Ramanujan represents someone who overcame many hurdles, and failure to overcome some of them, as I said before, would have resulted in a world that we live in today that I personally could not fathom. So how does the story end? It's rather unfortunate. Although Ramanujan would write 30 papers, some with Hardy, in his short time in England, the time was too short. He did this at a very difficult period in the world. This was the time of World War I. And of course, as an Indian, as I've mentioned earlier, he would have overcome great difficulties, overcoming racism. As a vegetarian, he would have been unable to eat the English food. Quite frankly, if you go to England, you know English food is really adapted Indian food. That's their best food, in my opinion. And despite all of these difficulties, Ramanujan was recognized as the first Indian scientist. Let me correct that. He was the first Indian scientist elected Fellow of the Royal Society. In 1918, he was awarded this great honor. By the way, I'd like to add a little tidbit. 2018 was only 2 years ago. 2 years ago, what marked the 100th anniversary of Ramanujan's election as FRS. And I was delighted when Venki Ramakrishnan himself, of Indian descent, he's a Nobel Prize winning chemist, he invited me to co-organize a celebration in London at the Royal Society, Carlton House. And many top scientists from all over the world representing many disciplines came, and we celebrated the 100th anniversary of Ramanujan's election. It was a very proud moment for us. It was a moving experience. And I'd like to emphasize that Ramanujan means a lot to the Royal Society. So much so that they took the opportunity to replace a coveted weekend workshop slot to honor Ramanujan, right? The Royal Society could spend all of their time recognizing past scientists and scientific achievements. They don't do this very often. And that sort of thing is reserved for people like Newton, Rutherford, and in 2018, Ramanujan. I was very proud of that. But this is a tragic story for Ramanujan personally. As you know, he became very ill during his time in England. He returned to India in 1919, hoping for a return to good health. And for whatever reason, that was not meant to be. And in April of 1920, he died at the very young age of 32. Despite that, despite his illness, some of his most important works, that's my personal opinion, were penned during this last year of life. If you've ever heard of the theory of the Mach theta functions, the period in his life in which he did this work was the last few weeks while he was severely ill. Now, as this is a public lecture, I don't want to go into too much of Ramanujan's technical mathematics. So let me pick and choose. Let me share with you one of my favorite theorems of Ramanujan because it clearly illustrates the power of creativity. This is a theorem that's related to just numbers. This is the work on integer partitions. And at first glance, this stuff of partitions could look like mere child's play. So to set the stage, let me give you an example of the partitions of the number 4. A partition is just the number 4 is any one of the 5 ways that one can represent the number 4 as a sum without reordering the summands. So here I've written down the number 4 in all of its possible ways as a sum of positive integers, including 4 itself. And in total, there are 5 partitions of 4. If you were to calculate the number of partitions of other integers, and here I've listed the first few powers of 2, 8, 16, 32, so on and so forth, you can count and discover that these are the number of partitions of those powers of 2. And what you see is that this total number grows very rapidly, right? And there are really indeed over 8,000 ways of partitioning the small number 32. And based on this set of numbers, you might ask, well, surely there's a formula, an elementary formula giving these numbers. Well, I regret to say that that is not true. And in fact, to give an indication of how far from true that is, let me tell you about one of the famous theorems that Hardy proved with Ramanujan, flushing out Ramanujan's speculation. They proved that P of n is asymptotic to this expression on the right, 1 over 4n root 3 times e to the pi root 2n over 3. Here e is, well, e, it's the base for the natural logarithm. Here pi is pi, the 3.14, so on and so forth. And what's crazy is that this elementary function about adding and counting, p of n, is nicely approximated by this incredibly complicated looking function, a function that requires both e and pi at the same time. This is not a trivial theorem. This theorem marks what's called the birth of the circle method. It's a fundamental tool in analytic number theory and harmonic analysis, and it was invented for the problem of the partitions. I first learned about this theorem as a high school student, and I was blown away by this theorem. You see, up to that point, I thought that all mathematical formulas were the stuff of tricks, the stuff that you learn in high school algebra, or maybe some of the theorems that you learn about in geometry, theorems that could be proven very quickly if you had the right idea. And this was the first glimpse that I had that, in addition to being kind of like an art, I recognized that art could also involve the development of a large machine. Very analogous to what one does in astronomy. If you want to make fundamental advances in astronomy, sometimes you need a brand new telescope. Every time a brand new telescope, one with more power, is developed, major advances are made. And the right way to think of this work of Hardy and Ramanujan is that their artwork, in this case, in terms of mathematical ideas, could be thought of as being analogous to making a brand new telescope, one which we're still perfecting to this day. So what do we learn from Ramanujan? So this lecture was entitled, Why Does Ramanujan Matter? Well, certainly we must have learned something from Ramanujan. And there are many answers to that. The first answer, which is paramount for a scientist, is Ramanujan's mathematical legacy, right? If the legacy wasn't really quite extraordinary, we wouldn't be talking about Ramanujan. So although I didn't go into much technical detail on this, I do owe it to you to tell you what his mathematical legacy includes. So in terms of mathematics, we learn a lot from Ramanujan. It turns out now that although Ramanujan was elected Fellow of the Royal Society for the 30 papers that he wrote in England, I think most modern day mathematicians will view the legacy of these papers and his notebooks in a very different light than they were viewed back in the day. It turns out that Ramanujan's notebooks and his formulas left many glimpses and clues for the mathematicians of his future. And it's my opinion that these glimpses amount to something even more astounding than the work that earned him the honors that he won while he was alive. This included inspiration for what are called the Weil conjectures that a Belgian mathematician by the name of Deligne solved, winning him the Fields Medal in the late 1970s. There's work that has inspired me that occurs at the interface of number theory and mathematical physics. It's called the subject of monstrous moonshine. And British mathematician Richard Borchards, now a professor at Berkeley, solved this conjecture, where one of the first steps in some of his work are the Hardy-Ramanujan formulas. And he won the Fields Medal in the late 1990s for this work. And of course, perhaps the most famous result in number theory in my lifetime is the proof of Fermat's last theorem by British mathematician Andrew Wiles. And Andrew Wiles, in his proof, makes use of a subject called the theory of Galois representations that was developed to explain Ramanujan's work from one of his 1919 papers. So this gives you scientific evidence for why I say that had Ramanujan's ideas never been brought forward, we would be presently living in a mathematical landscape that would be far behind where it is today. We have much thanks that we owe to Ramanujan. If you want to go beyond the stuff of pure mathematics or pure physics, string theory, and so on and so forth, which is encapsulated in some of the things I mentioned a moment ago, you might be answered, what do we learn from Ramanujan that plays a role in our everyday lives? Well, here's a picture of my friend P.P. Vaidyanathan. He is an electrical engineer at Caltech. In 2016, he won the Kirchhoff Award in signal processing. This is the highest award that IEEE offers in the field. What is signal processing? Very loosely speaking, signal processing is the engineering combined with the mathematics of transfer of information. So information is generally converted into waves, which have their own frequencies. These waves are captured, whether by satellite or satellite dishes, and so on and so forth. The mathematics and engineering of this idea, which is pervasive in the world today, requires deep mathematical ideas. One of the main hurdles in signal processing is that of error correction, right? If you receive a signal, how do you interpret it, taking into account that there may be errors that have entered through transmission? And what Vaidyanathan recognized is that in certain bandwidths, a new kind of mathematics was required to make these systems more efficient. And what he discovered is that there are functions that Ramanujan himself wrote down in his notebooks, which we now refer to as Ramanujan sums, that play a very important role in adding to the body of work developed by people like Fourier and others. And this is now put to use in the everyday applications related to information transfer. So Ramanujan matters because his ideas have found their way into the modern world in these very practical ways. So to finish, let me conclude with a summary, a synopsis of what the idea of Ramanujan is. Ramanujan was a man, but Ramanujan matters because he represents endless curiosity and also untapped potential. We all have to believe in this potential to proceed in the sciences. Science usually advances on the work of thousands over generations, fine-tuning and extending the scope of understanding. But from time to time, creative fireballs like Ramanujan burst onto the scene, propelling human thought forward. So one of the reasons The Man Who Knew Infinity was made is that Ramanujan was such a man. We want people to think Einstein. We want them to think Newton when they think and hear of the name Ramanujan. To conclude, there's no better slide for me to end this lecture with than this one. When we were traveling the world promoting the film, The Man Who Knew Infinity, one of our last stops before our theatrical release was in Silicon Valley in California. And it turned out that some significant donors helped support our film project. And so as a courtesy, it was an honor, actually, I shouldn't say a courtesy, it was an honor that we were asked to screen our film in Silicon Valley to the Breakthrough Foundation people. So we screened the film at Yuri Milner's compound. And what is the Breakthrough Foundation? The Breakthrough Foundation is funded by Mark Zuckerberg of Facebook, Yuri Milner, Jack Ma of Alibaba, and a number of others, high-tech gurus who support science. The Breakthrough Foundation gives out major prizes to top scientists around the world. And in fact, one of the leading string theorists is Indian, Ashok Sen. Ashok Sen is a recipient of one of these $1 million breakthrough prizes. And by the way, Ashok Sen recently published a paper making use of Ramanujan's work in black hole theory. I handled that paper. It was very exciting. But to make this story coherent, at the conclusion of our screening of this film to the Breakthrough Foundation, there was a question and answer session, and several people in the audience represented SETI. the search for extraterrestrial intelligence. And at the conclusion, I said something like this: just like the rest of you, just like SETI, seeking evidence for extraterrestrial life, we must search the globe for undiscovered scientific talent. It is here, it's on planet Earth. We must locate and nurture this undiscovered talent, because there are Ramanujans, we strongly believe, on Earth presently who have to be discovered, who could otherwise be lost or suffer from what could be perceived as the indignities of a very rigid educational system. And to my surprise, at the conclusion of that presentation, Andrew Sarrazin, who is president of the Templeton World Charity Foundation, approached me and said, "You are right, and I'm going to give you a lot of money to help support this search." So for the last 3 years, we've been searching the globe in what's called the Spirit of Ramanujan Global Talent Search, giving out little fellowships, little grants to those who have supreme talent, but otherwise might not have the financial backing to participate or have access to innovative educational programs, or have access to the internet, so on and so forth. And so Ramanujan matters because he has inspired some of the most influential philanthropists in the world to help make the world a better place. And so let me conclude with that. I would ask the Indian Academy of Sciences, if possible, to help promote the Spirit of Ramanujan effort. The website is spiritoframanujan.com. And so if you know someone who is very interested in science, not just mathematics, who could benefit from a small grant to participate in, that could help fund participation in an innovative program, steer them our way, have them apply, because we hope to award 30 of them worldwide each year. And with that, let me conclude. I hope you agree that Ramanujan matters. Thank you very much.
This was a fabulous talk. Okay, Shiv Kumar Manikam asks, what was Ramanujan's views on the notion of mathematical proof and the need for mathematical proofs?
Yes. So because Ramanujan was not trained in the rigorous, say, British system, which I strongly believe in, and I think we all believe in, Ramanujan at the outset believed that his intuition was sufficient for, he thought that was sufficient. He was satisfied by his mathematical intuition as proof. But of course, this changed over time. The papers that Ramanujan published in England had rigorous proofs. So this is something he came to understand and adopted fully shortly after his arrival in England.
Skanda asks, can Ramanujan's theory be used in real life? I know you already kind of partly answered it, but if you have any more input.
Oh, yes. So it's a question of what we mean by real life. When you go to the grocery store, can you use Ramanujan's ideas directly in an absolutely clear fashion? Maybe not, but underneath that, Ramanujan's ideas invisibly appear, certainly in terms of many applications where networks are required. Perhaps you've heard of the theory of Ramanujan graphs. So you can the theory of Ramanujan graphs is the idea that, how would you assemble an efficient network where information can be relayed between any 2 points in this network rapidly without overburdening the network with too many connections. So very loosely speaking, the theory of Ramanujan graphs addresses this question, and that's perhaps one of the most influential roles of mathematics of Ramanujan in your everyday lives that happens. It's ubiquitous, but you wouldn't know it. Ramanujan's ideas are playing a very important role in physics. Is that our everyday life? Maybe not. But certainly, I think these are important. And as I mentioned before, the signal processing, that is significant.
So they are ubiquitous, but we perhaps do not always see them in front of our eyes. Someone asked that, is it true that they have connections with black holes?
Oh, absolutely. I've been involved with this. So this is a very hot topic. In fact, this past semester at the Institute for Theoretical Physics in the United States, we had a whole semester on quantum modular problems in physics. Probably half of the lectures were in black hole physics, and Ramanujan's Mach theta functions probably appear in a third of those talks. So I mentioned Ashok Sen. He is a professor at the Harish Chandra Institute in Allahabad. He is a local Indian scientist who makes use of of Ramanujan's ideas in black hole physics, and he's one of the best in the world today.
Mrityunjay asks, in cell division, the sum goes like 1 plus 2 plus 4 ... I suppose what is meant is one cell becomes two cells, and then two cells become four cells, and so on.
Yeah.
Which is a negative value according to Ramanujan. What is the significance of negative value in biological world?
Oh, yeah. So it's a similar thing. So that's called the zeta of -2. So the significance of these formulas is that there's a function defined by Riemann called the Riemann zeta function, which is the sum over the powers of the positive integers n. So summation n to the s, or 1 over n to the s. And from ordinary calculus, if the power 1 over n to the s, if the power s is greater than 1, that the sum is absolutely convergent. So like the summing the reciprocals of the squares, 1 plus 1/4 plus 1/9 ... that converges to pi squared over 6. But if you want to sum the perfect squares, 1 plus 4 plus 9, etc., that diverges, it goes to infinity. But if you make the analogy that that's the value of the zeta function at -2, there's something called the functional equation, and which gives rise to what's called the analytic, which is given by the analytic continuation of the zeta function. And this makes use of integrals and the gamma function, and that is the proper way to view or come up with an adaptation of those formulas. So what is the significance? That is another example of what's called the process of analytic continuation.
I hope that answers the biology questions. We'll see whether he comes back to write anything more on this. Nisharg Shah asks an interesting question. Is it possible to have Ramanujanesque discoveries today?
Oh, I hope so. I have to believe that that is possible. So is it literally happening? Well, I can think of a few people whose ideas are that important. There's a recent Fields medalist. His name is Peter Schulze from Germany. He won a Fields Medal in 2018, and he has the qualities that resemble and offer the impact that Ramanujan had. So beginning at a very early age, he was producing mathematics that experts had a difficult time following, and quickly recognized that they had to learn. And I think Peter Schulze is probably one of the very few people in my lifetime who I would say has that level of Ramanujan-esque ideas. But like I said, most students in the world today mistake strength in science and math for accuracy and speed on exams, right? And that's not what we have in Ramanujan. What we have in Ramanujan is these flights of fancy, these incredibly beautiful ideas that others have been able to take up after his death to develop theories. And I have to believe these people exist, and I hope that we find them.
Okay, that's very optimistic. There's an interesting question from Sagar Mundal, who says that if you were Hardy, what would your responses be to Ramanujan?
Oh, geez. That's a great question.
Yes.
So it's difficult to answer that question because we live in the 21st century. I don't know what I would be thinking had I been raised in England in the early 20th century. But I would like to think that, I don't want to be critical of Hardy, because without Hardy, Ramanujan's ideas would have been lost to the world. But I would like to think that maybe I would have done a little bit better job in terms of, caring for his health, right? Ramanujan was sick in England, and Hardy, was kind of an introvert. He was a lonely man. He didn't have many friends. And in this way, perhaps Hardy's main failing for Ramanujan was caring for him as, and caring for someone who was desperately ill. And maybe he didn't recognize that. You see, try to imagine how further along we could be in science had Ramanujan lived a healthy, long life. Think about what it would have meant if Ramanujan could have returned to England in 1920, a healthy man. Think about what it could have meant if he could have spent 40 years, 50 years lecturing across India, across the world, spreading his ideas. That is a loss. So although we celebrate Ramanujan today, I do want to recognize that he died at a young age, and the evidence suggests that So I'm not a doctor, but people have studied the letters and have speculated that he didn't die from tuberculosis, but instead died of an amoebic infection on the blood, which I understand is quite easily treated had it been properly diagnosed. And that is difficult for me to escape.
Okay, Ken, your talk seems to have inspired students from various branches, because Amit Chakravarti asks, being a chemistry student, I want to know, can Ramanujan's theorems be used for understanding chemical reactions?
Oh yes. Great question. Some of my students, well, I don't want to start Googling here because it might not be, I might not find what I'm looking for very quickly, but the answer is yes. So some of my most recent PhD students on the side wrote papers in theoretical chemistry at Emory University with a professor James Kint, Kindt. So as a theoretical chemist, you might be interested in how molecules form under various conditions that cannot be produced in the lab because it's just too expensive. And so some of Ramanujan's ideas in partition theory have been put to use in terms of understanding the dynamics of molecule formation, where the mathematics and the computer simulations that they inspire have been used in theoretical chemistry. You can look this up. Look up the Kint lab, Kindt, and you'll see that Ramanujan's formulas on partitions form the basis of some very recent work. And that's just one example. I'm sure there are many others.
All right. So now we have found application in physics, biology, and chemistry. All right. Vaibhav Singh asks, what are your views about Ramanujan giving credit of his mathematical findings to the Namagiri goddess?
Great question. So I am not Hindu, and so it would be disingenuous for me to say too much about this. but I am a spiritual person, and I do believe that there's something very spiritual and enigmatic about Ramanujan. There's no denying that. And so I think I will leave it at that. Whatever Ramanujan's source was, it was clearly something very spiritual, something that I cannot explain. And for me, I think that's probably as far as I will speculate. So there's something quite magical about the source of his ideas, and whether it's Namagiri or something else, I think we can agree that it's quite magical.
Okay, we'll leave it at that. That is very magical. And magical, I think, by definition means that something that cannot be explained, at least. The next question that I can see is Shiv Kumar Manikam. Did Ramanujan teach any time? If yes, did he like teaching?
Oh, I don't have any evidence that he taught any proper courses. Tutoring, almost certainly, but maybe Robert Kenago has more information on that. I don't know. I don't think so.
Is any Akash Mishra, is any work still going on mock theta functions?
Oh yes, oh yes. I in fact I have a Zoom call in 30 minutes to talk about the mock theta functions. Still occupies a lot of my time, and not just me and my collaborators. There's a large group in Germany thinking very seriously about them. Mathematicians at Stanford and physicists at Stanford are thinking quite seriously about them. University of Chicago. So yeah, the mock theta functions continue to be a very hot topic.
Do you think another Ramanujan is possible?
Oh yes. Which is why do you still see my computer screen?
Yes, yeah. yes.
See my computer screen. I hope you can read spiritoframanujan.com. One of the reasons we have this program is because we believe there are other Ramanujans out there. You don't have to be as talented as Ramanujan, of course, to deserve support, right? We use Ramanujan as a symbol that represents this cause. So if you want to learn about this, we've given 46 prizes to people from all over the world, these red countries.
Right. So you clearly believe that there can be another Ramanujan, and that's why you are trying to discover them.
Yes.
Is there Tathagata Naik? Is there any work of Ramanujan on prime number distribution?
Oh yes. In fact, I just got a paper for I just received a paper 2 days ago by Peter Moret, who is at the Max Planck Institute in Bonn. And he is, in fact, revisiting Ramanujan's work on prime numbers in the first letter that Ramanujan wrote to Hardy. So what Ramanujan wrote to Hardy about the prime numbers actually had a mistake. The idea is beautiful, but he didn't have sufficient details to complete what he was claiming in his letter. And I'm excited to say that Moret is revisiting that letter, and so, yes. So to answer your question, in short, yes.
Interesting question. Did Ramanujan sometimes make mistakes in his calculations?
Oh, in his calculations. Oh, everyone makes mistakes in their calculations. So yes. Yeah.
But I suppose there was no mistake in his insights. Okay, maybe we should take one last question and then finish it off. Is there any work of Ramanujan in topology, is asked by Akash Mishra?
Yes. Oh my gosh. So, I don't know how many answers you would like to hear on that. So let me offer two. So, topology is the study of shapes, and one can study shapes a number of different ways. An algebraic topologist studies shapes algebraically, whereas a differential topologist begins to implement the ideas coming from calculus and analysis to study shapes. You may have heard of work on the Poincare conjecture, the solution of the Poincare conjecture by Perelman, which earned Perelman the Fields Medal that he didn't accept. That is one kind of theorem in this fundamental question in topology, which is as follows. If I gave you two objects, right, how could you decide whether those two objects are essentially the same? All right, how do you deform one object into another without intrinsically destroying the true nature of an object? Maybe you heard about the genus or a torus or things like that. In differential topology, we're trying to decide whether or not two objects can be related in a smooth, continuous way without introducing sharp corners and edges in maps. And Simon Donaldson won the Fields Medal in the 1980s for defining invariants that answer whether two four manifolds, this is the hard case, are diffeomorphic. The problem is these invariants that he defined are very, very difficult to compute. And very recently, through work of people like Greg Moore and Ed Witten is he's a Fields medalist, but he's a theoretical physicist at the Institute for Advanced Study at Princeton. They found a way to make use of Ramanujan's Mach theta functions to study these Donaldson invariants in various settings. So to answer your question, yes. So if you want to study diffeomorphism classes of four manifolds, Ramanujan's Mach theta functions could be useful to you. And in one other direction, if you want to study invariance in knot theory, there's a subject called the theory of quantum modular forms, which includes Ramanujan's examples, some of Ramanujan's examples as the prototypes. Now this is a very hot topic, to use Ramanujan's Q series to study and define knot invariance. And this is related to the work of, well, many people. So most recently, Vaughan Jones, who won the Fields Medal for defining what are called the Jones polynomials. He passed away recently, but among his last projects was this sort of connection. So yes, if you work in knot theory and if you work on four manifolds, you might benefit a lot from using Ramanujan's functions. Very good question.
There are many questions. One of them, I will mix some of them. It is basically how many of his notebooks, the works of Ramanujan, how many of it have been proved or disproved, and how much more is yet to be worked on. So basically, people are asking whether there is work that can still be done based on Ramanujan's initial work.
Yeah. So two related questions with two very different answers. There are mistakes in the notebooks, but who doesn't have mistakes in their notebooks? I don't think there are any significant mistakes in the notebooks. So every formula that in the notebook, if it's not correct, is correct in principle. In some instances, the equal sign meant to Ramanujan something very different from what it means to you and me. If we say A equals B, we agree A and B are the same thing. But often in Ramanujan's notebooks, equals could just mean that there's an interesting relationship between the two quantities. So from that perspective, there are perhaps almost no mistakes, okay? I think all the formulas in the three notebooks have been commented on with commentary largely through the work of Bruce Byrne and George Andrews. But please don't mistake that by saying we understand the notebooks, right? If you can check a formula, that doesn't mean that you understood why Ramanujan wrote the formula down in the first place. It just meant that you could confirm something is correct. And this is perhaps the deeper question, right? How often has it been the case that you feel like you've mastered a subject only to go back to it later and recognize through the lens of maturity or through the lens of just knowing a bit more that you've come to a deeper understanding of a subject you once thought you mastered. Well, that happens all the time. If you are a graduate student, you may master a course. You teach your first course, you feel like you know it. But if you teach it 10 years later, there's a very good chance the course you teach 10 years later is better because you understand the subject better. That is the perspective that we have to adopt with Ramanujan's notebooks, except not 10 years later, we're talking 100 years later. We don't have the luxury of asking Ramanujan how he arrived at his formulas. In some cases, we have to believe, and in some cases, we've even learned that he had master formulas that he didn't write down in his notebooks, only to be discovered later that were even deeper theorems. And so I think the challenge of understanding the true legacy of Ramanujan's notebooks will never end, because all good mathematics leads to deep structure, and some of these deep structures lead to even deeper structures, and that process is the process of science, and that will go on indefinitely.
Thank you very much, Ken. You have said yes, when your answer has been yes to so many questions that people have asked whether there is application in physics or biology or chemistry or astrophysics, and you have always managed to answer yes. So Ramanujan's work, it's kind of overwhelming that in how many places Ramanujan's work finds applications. So you said there is a meeting at 10, and which is some 20 minutes away, I guess.
I have to go,
so,
right, yes.
Thank you very much for your time, for your precious time. We are very grateful so much time on it, and you have delivered a fabulous lecture. I suppose you can see the YouTube comments, and you will see that how many people have actually said, some people have said that they want to be your students just by listening to this lecture. All right.
Thank you very much.
It has clearly been a very motivating lecture.
All right. Well, my pleasure. All right.
Thank you very much again on behalf of the Indian Academy of Sciences and the Academic Trust. I thank you again.
Okay, thank you. And I hope to visit maybe in 2021 sometime.